Hi, everyone. Today we're going to look at some optimization problems. These tend to be of a trickier nature. We also get to look at Calculus Dog today um, and, uh, and see if we can apply our optimization skills in these situations. This first problem is actually a problem that showed up on the AP exam in the free response a few years ago. We're told that we have 20 inches of wire, and that we're going to use this wire to make a square and a circle. And this is a 20-inch piece of wire. Okay, so we're going to make these shapes out of this piece of wire. And what we've been asked is, where should we cut the wire to maximize area? Okay, that's what we're trying to do, maximize area. And what area? The total area of both the square and the circle. Okay, so we want to add the area of the square, add the area of the circle, and get a total area, and we want that total area to be maximized. So I know what equation I need to take the derivative of. I need to take the derivative of my area equation, and it's the total area equation, not the area of the square or the area of the circle, but the total area. All right, so let's see what we can do with this information. We've got a piece of wire. It's 20 inches long, and we're going to cut it someplace. And I'm going to call this amount x and this amount 20 minus x. Okay? And now I'm going to pause for a moment while I check the settings. All right, settings are great, so here we go. Let's continue with this problem. Okay, so I'm going to use this piece of wire to make the square, and I'm going to use this piece of wire to make the circle. Now, when I talk about making the square, I'm actually going to be folding this piece of wire to make a square. And this will have S, 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 or 4S is this amount of wire. Well, I know this amount of wire is also called 20 minus X. And over here, I can do the same thing with the circumference of the circle. The circumference of the circle, I know, is 2 pi r. And if I'm going to make that circumference of the circle, I've got this many inches of wire to do it with. But I don't need circumference and perimeter. I need areas. So I'm going to have to get not only the area of the circle and the area of the square, which are pi r squared and s squared, but I also need these areas in terms of the same variable. Remember, I was asking in class, is this thing that I'm taking the derivative of in terms of one variable? Well, if I added this area to this area, right now my total area would be in terms of radius and side length. I need something in terms of just one variable, one area function in terms of one variable. And I think I see, since both of these have x's in them, I can solve this equation for x, for s rather, for 4, and get that side length is 5 minus 1/4 x. And over here, I can say that radius is x over 2 pi. Now, what am I going to do with those values? I'm going to plug those values into their respective area formulas. Remember, area of the square was side squared, and in our case, that would be 5 minus 1/4 x squared. And if I FOIL, I'll get the area of the square to be 25 minus 5/2 x plus 1/16 x squared. Now I want to repeat that process over here with the area of the circle. Remember, the area of the circle is pi r squared. And by the way, if you don't remember these formulas, you should be writing them down on your formulas I've forgotten page so that you don't forget them again. Okay, so what do we know about radius? Radius is x over 2 pi. So I'm going to take this radius and I'm going to replace with x over 2 pi. So area equals pi x over 2 pi squared. And I get that area of the circle then is pi x squared over 4 pi squared. And I can cancel a pi out on top and a pi out on the bottom. And so then the area of the circle is x squared over 4 pi, and the area of the square is 25 minus 5 halves x plus 1/16 x squared. So if I'm looking for total area, I've got 25 minus 5 halves x plus 1/16 x squared plus x squared over 4 pi. Woof. Okay. So what do we do? Are we done? Can we set this equal to 0? No. We still haven't taken the derivative of this yet. We need to know a prime in order to find when area is maximized. So let's find the derivative. The derivative of this is 0. The derivative of this is negative 5 halves. The derivative of this is 1/8 x. And the derivative over here is the 2 will come down, and I'll have plus 1 over 2 pi x. Okay, so there's my a prime. And I notice that a prime is linear. Look, it's a thing times x plus a thing times x. This is a linear equation. This is y equals mx plus b. Is that ever undefined? No. So I don't have to worry about undefined here. I do have to set a prime equal to 0. And when I do that, I get 5 halves equals 1/8 x plus 1 over 2 pi x. Now, at this point, I'd love it if you were comfortable enough to say, oh, I can factor out an x. And what are we going to have then? 1 over 8 plus 1 over 2 pi equals 5 halves. And I think rather than dividing both sides by this, I'm going to make a common denominator over here. This will get multiplied by 4 over 4. This will get multiplied by pi over pi. And we'll be able to say pi plus 4 over 8 pi x equals 5 halves. Why did I want to do that? Well, now solving for x is just a matter of multiplying by the reciprocal. Which was 8 pi over x plus pi. Oops, pi now. 4 plus pi. Okay, so these will cancel, and I'll know what x is. And over here, I guess I can cancel this with this, giving me 4. And we'll have 4 pi over 4 plus pi. What do you think? Can I cancel those pi's? Can I cancel those 4's? Don't you dare. So instead, don't forget that 5. So instead, what we're going to do is decimalize this on our calculator. So let me pick up a calculator now. We've got 20 pi divided by parentheses 4 plus pi. And I end up with x is 8.798 inches. So great. So when x equals 8.798 inches, I have a critical point. Now, we're supposed to check for maxes and mins in 3 places. Derivative undefined. This linear derivative is never undefined. Derivative equal to 0. That happens here. And then what about the third place? Well, that's the endpoints of our bounded interval. And we have a bounded interval in this situation, don't we? We've got 0 and 20. So 8.798. But we also want to check the endpoints of our bounded interval as well. Remember, this is an A prime sign chart. And what was A prime again? A prime was, back up here, A prime was, I like the factored version of this. Um, Pi plus 4 over 8 pi times x. Pi plus 4 over 8 pi times x equals 5 halves. Okay, so if I plug in a number like 0 over here, I get 0. And since 0 is less than that, I know this is a negative. And if I plug in a number bigger than this, like, I don't know, 3 pi, 3 pi will work. The pi's will cancel, and I'll have 3 plus, oops, I'll have 3 times pi plus 4 over 8. And is that greater than or less than 5 halves? Well, I'm not so sure. Let's see. This is about 7. 7 times 3 is 21. 21 divided by 8. 3 plus pi plus 4 divided by 8. And that equals 2.67. And since 2.67 is bigger than 2.5, I know I have a positive here. And so look, indeed, what have we found? Area is minimized when x equals 8.798. Well, but our question was, when is area maximized? Uh-oh. Where are our maxes? Well, our maxes in this problem are at the endpoints. So, because from this point, x equals 0, the area function decreases. So I know area is a maximum at 0. And from this point up to 20, area is increasing. So area is increasing to a maximum at x equal to 20. So I've got maxes at 0 and 20, which means I need to go back to my area function and plug in a 0 and plug in a 20. Okay, what was my area function? Well, my area function, you may recall, was 25 minus 5 halves x plus 1/16 x squared plus 1 over 4 pi x squared. Was it 1 over 4 pi x squared? I'm sorry, I want to go back and check that. Hold on. Area. Yes, 1 over 4 pi x squared. There it is. Okay. So I'm plugging a 0 in for all of these x's. A of 0. Well, that's easy because this goes away, this goes away, this goes away, and we get 25. So area is 25 when x equals 0. Now remember that x represented the wire that we were using for the circle. So the implication here is all the wire for the square and no wire for the circle. Okay. What if we plug in a 20? What do we get? Ugh, really? I don't want to do this by hand. Well, remember, this was something we FOILed. It was 5 minus 1/4 of x squared. Plus here, I don't mind plugging the 20 in. 20 squared is 400, so we get 400 over 4 pi. Okay, so what happens here? 1/4 of 20 is 5. 5 minus 5 is 0. Oh, that all cancels out. Well, that's convenient. And here we get 400 over 4 pi, which is 100 over pi, which I believe is bigger than 25. Let's check that. 100 divided by pi, and I get A of 20 equals 31.831 square inches. Aha! That's my max. That's my absolute max. Absolute max then comes when x equals 20. X was the wire that we were using for the circle. So this implies that we use all the wire for the circle and none for the square. And why was it that so many students were really upset with this problem when it showed up on the AP exam? Because the problem said, where are we going to cut the wire? And it turns out that, in fact, to maximize the total area, we're not going to cut the wire at all. We're just going to use all of the wire for the circle. Yeah, so welcome to the AP. All right, there's our first question. Let me take a pause for a second, and then we'll get the second question going. Okay, let's continue. Um, I'd like to look at a problem that has an interesting story attached to it. It's all about Calculus Dog, the dog who does calculus. I'd show you a picture of him, but I don't feel confident that I could do that without screwing up the video. So you'll have to wait until I get back for me to show you this picture of Elvis, the uh, calculus doing corgi. Um, Here, I have a little article for you. Tim Pennings, a math professor at Hope College, was playing on the beach with his Welsh corgi Elvis when he noticed something remarkable. Elvis was doing math. The dog wasn't ciphering with a calculator. Rather, he was acting out the solution to a calculus problem. How exactly did Elvis show a knowledge of calculus? Pennings was playing fetch with Elvis that day, throwing a ball at an angle far into the surf. To retrieve the ball, Elvis might have taken the shortest route and swum right for it. But a dog can run much faster than it can swim. So to get the ball in the shortest time, Elvis ran along the beach for a certain distance before plunging into the water and swimming the rest of the way to the ball. So it says that several days later, Pennings tested his observation by taking Elvis back to the beach and clocking the dog's running and swimming times. Then Pennings tossed the ball into the water 35 times over the next 3 hours, each time measuring both the distance to the ball and the distance Elvis covered on the beach before jumping into the water. We stopped only when the waves got too high, Pennings told Current Science. Elvis had no interest in quitting. Back at the office, Pennings plugged the measurements into a formula that revealed where on the beach Elvis should have jumped in to the water in order to minimize his retrieval time. The spot changed position with every throw because of the angle and the distance the ball differed each time, but Elvis came within a foot of the spot on most occasions. So, it's our turn to see what it is that Elvis is doing instinctively when he plays fetch. So let's look at a situation. We've got Tim over here, and Tim throws the ball into the water. There's the ball. This is the line of the beach in the problem. And we notice some different things here, like the dog could swim directly to the ball. This is the shortest distance, but it's the most amount of swimming. And corgis don't swim very well. So this isn't very attractive, even though it's a shorter distance than this plus this. Elvis isn't interested in this. Too much swimming, says Elvis. So then look at this option. Run down the beach until you're perpendicular with the ball, dive in and swim directly to the ball. This is the shortest swimming distance we learned in geometry, but it's also the longest running distance. So Elvis doesn't do that either. Instead, what Elvis does is runs down the beach a little bit, changing each time, and then dives in and swims the rest of the way. And so what we want to figure out is we want to minimize time, specifically Elvis's retrieval time. Okay, so let's think about a problem. We've got, let's do a small throw here. This is 8 meters this way and 3 meters this way. And let's call this distance x, so this distance can be 8 minus x. Now, 8 minus x represents the distance the dog is going to run along the beach. And you may say, hey, Mr. Gukler, why didn't you put the 8 minus x over here and put the x here? Because this is the distance the dog runs on the beach. There's a reason for that, and it'll come up in the moment. Okay, Now I've labeled the picture. Oh, there's one other thing I need. I need to know this length here. I need to say something about this. This is the distance that Elvis swims. And I see here a right triangle. And with the Pythagorean theorem, I can find this missing side length. Now notice I've just got an x to square and a 3 to square, and that's not so bad because then the hypotenuse is 9 plus x squared. But think if we had put this over here. Ew, I don't want that under the radical with my 9. So we're going to stop here. So we've now got, this is the distance in the water, this is the distance on the land. Do we add them together to get total distance? Well, we're not trying to minimize distance. If we were, we would just go here. But Elvis doesn't go there. That may be the minimum distance, but Elvis doesn't swim so good. Elvis wants to minimize time. We need to write time equations. So let me give you a little more information. Elvis can run at 6 kilometers per hour. Oops, let's make that in red so that you equate it with a land experience. Okay, so land, Elvis runs 6 kilometers per, no, sorry, that's swimming speed. No wonder it was blue. 8 kilometers per hour. And Elvis swims at 6 kilometers per hour. Well, you may be saying, how does that help me, Mr. Kukla? I've got distances now, I've got these rates now, but you telling me I need to minimize time. Sure. So remember from middle school, distance equals rate times time. Okay, we want to know what time is, so we divide both sides by rate. So time is distance over rate. Now in our problem, that means we've got the time on land, which would be the distance on land over the rate on land. And we've got the time in the water, which is the distance in the water over the rate in the water. So let's put all that information together now to get a total time equation. Total time as a function of x is going to be the land distance over time, that was 8 minus x, distance over rate, and the rate was 8, plus, what can we say about the water experience? Well, we know the water distance is square root of 9 plus x squared, and the water rate is 6. So here's time as a function of x. And the first time you do one of these shortest time problems, it's a little intense trying to get that equation. But remember, ultimately, we're just using distance divided by rate to give me time and adding those two times together. So if I'm looking for minimizing time, I want t prime. I'm going to take the derivative. Now, because of this, I don't want to play that game. Let me do a little simplifying first with t and split this into two fractions, 1 minus 1/8 x. And then I'm going to rewrite this as 1/6, 9 plus x squared to the 1/2. Okay? This is the thing that I want to take the derivative of. So t prime is going to be equal to negative 1/8 because the derivative of 1 is 0, and the derivative of negative 1/8 x is negative 1/8. What about the derivative here? I'll bring down the 1/2. I'll get 1/12, 9 plus x squared to the negative 1/2. Don't forget that negative 1/2. People are still doing that. They're starting the power rule and forgetting to subtract 1. And don't forget chain rule. We need to take the derivative of this inside function, 2x. Okay, so here's t prime. And I can tidy t prime up a bit, which may be useful to see certain things, namely 2x over 12, 9 plus x squared to the 1/2. Namely, that this is never undefined. Here's my derivative. My derivative would be undefined when this denominator was undefined, but this will never be undefined. Look, if I plug a negative in here, squaring makes positive, plus 9, always positive. If I plug a 0 in here, I'm still adding 9, I still have a positive. And when I plug a positive number in here, positive squared is positive, plus 9 is still positive. So this derivative is never undefined. I only need to worry about then derivative equal to 0 and any endpoints. Yes, there are endpoints. Let's go back and look at the original picture. In our original picture, we see that this length is 8 meters. So we can start at 0 meters. We could go to 8 meters. So our boundaries are 0 and 8. We know that Elvis isn't using those, but those are endpoints that we still need to consider. Okay, so let's set this derivative equal to 0. And we'll add 1/8 to both sides and get, and some canceling, and get x over 6 square root 9 plus x squared. And if I cross multiply now, 6 square root 9 plus x squared over 8 equals x. I guess I could do 3/4 here. And I'm going to square both sides. Some people like to isolate the radical before squaring, so maybe I should make them happy. Cancel out those, and we get the square root of 9 plus x squared equals 4/3 x. Okay, to undo that radical, I'm going to square both sides. So I get 9 plus x squared equals 16/9 x squared. I'll subtract x squared from both sides. I'll get 9 equals 7/9 x squared. I'll multiply both sides by the reciprocal, 9 over 7. And I'll get x squared equals 81 over 7, or x equals 9 over root 7. Okay, 9 over root 7 meters. We've got 0 meters, we've got 8 meters, and we've got 9 over root 7. Let's take a look on our calculator where that is. But I need to pause for a second. So let's pull out a calculator and figure out where this is. 9 divided by square root of 7. Oh, no, that wasn't it. 9 divided by square root of 7. It happened again. Stop it. Okay. And I get this is approximately 3.402. So I want to test on either side of that in A prime. No, in T prime. This is a T prime sign chart. So I'm going to test 1, and I'm going to test 8, or 0 and 8. Let's see. Back to T prime. Here's T prime. T prime equals negative 1/8 plus 2 over 6 square root 9 plus x squared. Okay, if I plug in a 0, I get 0 here. Square root of 9 is 3. 3 times 6 is 18. 2 over 18 is 1 over 9. So I've got negative 1/8 plus 1/9. Well, this is not big enough to undo that, so I've got a minus on T prime. So minus. And then I want to put in something on the right-hand side of 9 over square root of 7. So we'll go back to T prime, and we'll say, what can we plug in that makes sense here? I like 4. 4 is bigger than 3.402. So 4 squared is 16. 16 plus 9 is 25. Square root of 25 is 5. 5 times 6 is 30. So I've got a 30 on the bottom. And on top, remember I'm plugging in a 4. I've got 4. 4 over 30 is 2 over 15, which is 1 over 7.5, which is bigger than 1 over 8. And so I do have a positive value over here. So yes, I do have a minimum. time is minimized when x equals 9 over root 7 meters. And don't forget your justification, because to the left of x equals 9 over root 7, t prime is less than 0, and to the right of x equals 9 over root 7, t prime is greater than 0. Yay, Elvis, the calculus doing dog. Okay, so that's the second problem I have for you today. The third one that I'd like to look at involves your job as a holiday elf in Santa's workshop. Let's take a look at this problem. Pokemon is still a thing, and because Pokemon is still a thing, um, the Holiday Workshop has an order to produce the new Pokemon. And maybe the makers of Pokemon are getting a little tapped out for ideas, because this one is called Conio. Conio is a sedentary cone-shaped Pokemon, and we're trying to figure out the largest conio that can fit in our 3-inch radius Pokeballs. Okay, so I'm trying to shove that inside of that. Now, clearly I can make a conio that's bigger than this one. So how big is the biggest one I can make? Well, we're told that the Pokespheres have a radius of 3 inches. And a common mistake that students make is that they make this be the cone that goes inside. And there's only one cone that goes inside in their mind, and this will be the largest one. Well, it turns out this isn't the largest one, and by drawing it in this manner, they force their brains to confirm, in fact, that the thing that's not true is true. So don't draw the cone this way. Instead, let's take that blue out, and let's draw this cone. This is a more general cone. But notice the radius of our conio is no longer the radius of the sphere, right? It's got its own radius down here. Here's our radius of our cone, which I'm going to use a little r for. And here we have a height to our conio. And you may recall we're trying to maximize the volume of the cone. The volume for a cone, I'm sure you remember, is 1/3 pi r squared h. And if you didn't remember that, you definitely need to know that by the time we have our next test. Don't expect it to be given either on a test or the AP exam. You need to know your formulas. Okay, so this is the thing I'm going to maximize. And of course, at this moment, it seems appropriate to say, hey, is volume in terms of one variable? Oh, look, it's in terms of two different variables, and I really need to get volume in terms of one variable before I take this derivative. So I need to do some thinking. And here's what I'm thinking, and this is why we go to class, because this is not the sort of thing, unless you're an ancient Greek or someone who lived in ancient Alexandria, you probably think of on your own. You see someone do it first. So this is the radius of the sphere. This is 3 inches. Well, I can also draw the radius of the sphere this way. This is also 3 inches. And you might be saying, sure, but why did you do that? Well, remember, I know that this is the radius of the cone, and I'm going to call this length, because it's vertical, I'm going to call it y. I'm not going to call it h, because I'm saying h is this whole distance. H is equal to y plus 3. Okay, and radius, can I say something about radius? Well, I know that radius squared plus y squared equals 9. So I know radius squared equals 9, minus y squared. Where did I get that from? Well, see, there's a right triangle here. And so I can use the Pythagorean theorem with that right triangle to help me find that r squared is 9 minus y squared. Well, conveniently, I don't need r, I need r squared. And here's my h, so I'm going to plug that in. So I can rewrite volume. It won't have an h, it won't have an r, it'll only have y stuff in it. So what will my volume formula look like? We started off with 1/3 pi r squared h. We said that r squared was 9 minus y squared, and we said h was equal to y plus 3. Okay. Grant likes foiling these out, so pi over 3 times negative y to the third minus 3y squared. Um, this times this times that, plus 9y plus 27. Okay, and this is a constant times all of that, so I know the derivative of a constant times some stuff. Here's volume prime, will be that constant times the derivative of this volume polynomial. So the derivative of the volume polynomial is negative 3y squared minus 6y plus 9. In fact, I notice I can factor a negative 3 out of here. So if I pull that negative 3 out, there's still a pi over 3 out in front. We get y squared plus 2y minus 3. And so here's our derivative. Okay, so I want to know, derivative. I want to know when this derivative is undefined. Well, this derivative is never undefined. This derivative is, in fact, a parabola, so it's defined everywhere. What about derivative equal to 0? So 0 equals negative pi y plus 3 y minus 1. Well, does negative pi equal 0? No, that doesn't play a role in finding y values. This is just a stretching factor. What about here? Y plus 3 equals 0. Y equals negative 3. Well, remember where y was in our picture? Can we have a y value of negative 3? Look here in the picture. Here's our y value. Can that be negative 3? No, it can't. So we're going to get rid of that, and we're just going to have y equal to 1. So I'm going to make a v prime sign chart and put y equal to 1 on it. And I'm going to test something to the left and right in v prime. Okay, so remember what we had for v prime? V prime was negative pi y plus 3 y minus 1. That was v prime. So if I plug a 0 in here, I get 3 times negative 1, negative 3 times negative pi is positive 3 pi, so I have v prime as positive here. And if I plug in a 4, I get 4 minus 1 is 3, 4 plus 3 is 7, so I get 3 times 7 is 21 times negative pi is negative 21 pi, or negative. So I see that volume of the cone is maximized when y equals 1, because to the left of y equals 1, v prime is greater than 0, and to the right of y equals 1, v prime is less than 0. Now, Megan cautions us to watch out. Did the question say what are the dimensions of the largest conio that we can make? Or did it just ask us to maximize the volume? Oh, have we even found the maximum volume yet? All we did was figure out a y value that would create the maximum volume. So we still have, I feel, some stuff to do. Remember, r squared was equal to square root of 9 minus y squared. And so in our problem, r squared equals the square root of 9 minus 1, or r squared equals the square root of 8. And that's r squared is the square root of 8, which I guess I can write as 8 to the 1 half, which is 2 to the third to the 1 half, or 2 to the 3 halves. And you might say, why are you doing that, Mr. Kukla? Well, because I need to take the square root of both sides over here and over here. And so I know that when r equals 2 raised to the 3/4 power, now what about h? H was equal to y plus 3. That's a little easier. 1 plus 3 is 4. So when radius equals 2 to the 3/4 and height equals 4, volume is maximized. We have the dimensions, and we can plug these values back into our volume formula if the question had said, what is the maximum volume? Okay, so these were three pretty exciting problems. You might want to watch them again. There are some others that I thought we might do, but I think I'll hold off on them and give you the rest of time in class to work on these problems that you received on the worksheet. Okay, well, have fun with those. Have a wonderful Thanksgiving. Don't forget to send me your questions via the GroupMe. Okay, bye-bye.